All right, yeah, please take your seats. So far, everything we've seen today, including the material science, chemistry, and battery problems, all of those were mostly language-based models, right? So the tokens were pretty much discrete alphabets. But there's a whole range of physics that goes beyond language representations, and that is, one manifestation of it is spatio-temporal physics. So Kaustubh is going to walk us through PhysicsNeMo, which I think is very widely used by the CA industry. So thank you very much again.
Thanks, Dr. Duraiswamy, for the introduction. Yeah, my name is Kaustubh. I'm a yeah. You guys can hear me okay? Louder? This is better?
The mic on. The other thing you can do is, take one of these.
Okay.
Okay.
All right. Can you guys hear me better?
Yes.
Okay. Thank you. So yeah, thanks, Dr. Duraiswamy, for the introduction. My name is Kaustubh, and today I'm going to be talking about the AI approaches for spatio-temporal physics, and more specifically, how we are handling them using PhysicsNeMo framework that we are developing here at NVIDIA. So thanks everyone for attending, and let's get started. So in terms of the agenda, so this is what we're going to talk about today. We'll go over a little bit of motivation behind using AI approaches in physics, physics-based modeling. We'll look at how at NVIDIA we are accelerating some of these approaches, and then we'll dive deep into a couple of use cases and see how some of these things work in practice. More specifically, we'll cover the external aerodynamics and the weather and climate work that we have been doing for about 2 to 3 years now. And then we'll follow it up with some deep dive into the code and followed up for resources and discussion, right? So with that, let's get started, right? So I think most of you guys here are probably aware that simulations are critical for scientific analysis and engineering decisions, right? So a lot of product design or a lot of engineering analysis requires analyzing systems, and it has evolved over the years. Initially, you had these experimental setups that one would do, and soon they turned out to be expensive, costly, and so there were these numerical models that were developed, which allow you to do these simulations, replicate the experimental setup through simulations. And they provided a order of magnitude speed up in terms of what you could achieve. But even to we have come a long way since then. But even now, even those methods are getting computationally expensive as the amount of designs that we want to analyze, as the problems domain sizes increase, as the complexity increases. And so what we are going to look at today is how NVIDIA technologies can help to accelerate some of these workflows, right? So how can we create better products? How can we create a better digital twins? Something that can allow real-time capability, and that also has ability to ingest data from variety of sources, be it sensors, experimental observations, simulations, so on and so forth. So I'm going to talk about a little bit from the spatio-temporal physics aspect, right? As we saw in the previous talks, we discussed a lot of ways in which NVIDIA is involved in accelerating some of the LLM research. But in general, in terms of like on the physical sciences standpoint, right? We are working on accelerating these workflows through two different approaches, right? So we have these GPU accelerated math libraries, which take advantage of really fast matrix computing capabilities of GPUs. And so they offer a drastic amount of speed up when compared to your CPU math, right? So you have libraries like AMGX, QSolver, Warp, QBlast, so on and so forth, which are really designed to do some of these matrix-based operations very fast on GPU, and they can be used in your custom workflows. You have Pythonic as well as C++, Fortran-based libraries here to do that. On the other side, you have GPU acceleration via AI models. And so this is where libraries such as BioNeMo and PhysicsNeMo come into picture, right? So BioNeMo is this drug discovery framework. And then what we're going to talk in today's um, session is this PhysicsNeMo, which is the physics driven framework for developing physics AI models that we are developing here at NVIDIA. So what is PhysicsNeMo? So as I mentioned, PhysicsNeMo is NVIDIA's AI framework for developing these physics AI models, so models for the physics AI space. Um, with PhysicsNeMo, we aim to provide a toolkit to develop solutions that obey first principles and domain knowledge, so models that can be applied to problems such as in engineering and engineering and science in general. And the goal here is, like with every other library that we develop here at NVIDIA, is to provide a state-of-the-art performance for solving some of the really industrial scale, large scale problems. So that's some of our goals here. And so what on the right here, we have a bar chart representing speed ups that we have observed across variety of domains. We'll dive deep into some of these domains as we go through the presentations. But we have we have seen. Let's take external aerodynamics as an example. We have seen about 8x or 8x to 6x speed up when we go from just the CPU based math to like GPU accelerated math that we talked about through the other NVIDIA CUDA libraries, and then a further 2000 or about a couple of orders of magnitude speed up when you go to through like AI-based surrogate models, and what they really are. We'll talk more in the subsequent slides. So diving a little bit more in detail. So what is PhysicsNeMo, right? So PhysicsNeMo, this is what the software stack for PhysicsNeMo looks like. So we try to provide multiple toolkits for people to integrate some of these workflows in variety of different capacities in their simulation and design and analysis workflows, right? So we have these NIMs and inference pipelines which deal with like the inference of a model. So assuming that you have a trained model or some of the trained models that we ship, we provide these utilities and the model checkpoints that one can take in and just run inference on without worrying about the training aspect of the model. A big portion of PhysicsNeMo is providing utilities to develop these training pipelines. As we will see in subsequent slides, a lot of the applications in this area are very domain specific. So it's a bit hard to have something very general, for across a wide different applications, especially if you think of like something like CAE, where you could be analyzing cars or electronic cooling or so a variety of different things. So training is a huge aspect in some of these things, and our goal is to provide um, you know um, domain specific models through a wide variety of model zoo, GPU accelerated training pipelines which allow you to read and write data across these formats, and also utilities to inject your physics based knowledge, be it through implicit constraints or through explicit constraints um, about the geometry, the partial differential equations that govern the system, and so on and so forth. Um, and with all of this, we want to ensure you get the best performance of your GPUs, right? So everything is geared towards you know optimal speed, memory optimizations, ability to scale across multiple GPUs, multiple nodes as the sizes of these problems increase. And we also provide a lot of reference applications so that users can build on top of. So the goal is to democratize AI applications in this area. And so we provide some reference applications as well. In terms of fundamentally, in terms of software stack, we build on top of a lot of other NVIDIA technologies and NVIDIA accelerated libraries, right? So we build on top of libraries such as DALI and Warp. DALI is a library at NVIDIA developed for fast GPU data loading. So, loading the data from your disk to GPU memory is a time consuming process, and the DALI library aims to optimize that, and we leverage that to build some of these super optimized data loaders. Um, Warp is another framework to build fast GPU kernels for some of the common operations, and so we have some fast GPU kernels like nearest neighbor search or ball query algorithms and many other things that leverage this Warp framework. And of course, we build on top of the GPU optimized PyTorch itself. So PhysicsNeMo, as we will see in the subsequent examples, is a framework built on top of PyTorch. It's aimed to complement PyTorch and interoperate with PyTorch, right? So we build on top of the GPU optimizations that have gone into the PyTorch as well. So that, in a nutshell, is the PhysicsNeMo framework. Um, I alluded to the providing a model zoo, and so I want to dive deep uh, over about that here. So we provide a wide different access to different models that are specifically suited for this physics AI applications. And some of these models, we have tried and tested across multiple different domains, and made sure that stress tested those models and those kind of things. And so here we are like I'm showing a few of them that are part of this toolkit, right? So we have a variety of models that can work across fully data driven or physics driven. In this space, there is a concept of you have physics on physics, and then you have data. So and what I'm representing here on this plot here is how these models are spread across these two axes. So when I say physics, these models typically don't need any training data in uh, to train them. And by that, what I mean is you don't need any training data coming from, let's say, other simulations or other experimental data. Like these models can solve your fundamental partial differential equations through some optimization techniques. So that's the axis on physics side. And then you have data where you are operating with the data coming in from different simulations, different experiments, and you are training models to capture the physics from there. And so we aim to provide models that work across this spectrum. So some of these models have some inductive bias about the problem built into them. So, things like these operators are in that category, right? Like you have things like Fourier neural operators or spherical Fourier neural operators, which try to encode the spherical geometry into the architecture. And we have found that that model performs really well for like some weather applications, which we will see in the rest of the presentation. And so we have a few models along those lines. We have graph neural networks that are applied for meshes. A lot of simulations done in this space are done on like finite element, finite volume meshes, and graph networks have been shown to be very useful in representing those type of unstructured data formats. You have a wide variety of diffusion models as well, and a few other domain specific models. So in terms of summarizing the features, what PhysicsNeMo provides, it builds on top of PyTorch. So a lot of the utilities from PhysicsNeMo are going to be interoperable with PyTorch and are going to complement PyTorch. So not replacing the PyTorch framework, but the idea is to drop in utilities and tools from PhysicsNeMo into your own PyTorch-based workflows. We provide performance enhancements. So, things like CUDA graphs, kernel fusions, JIT compilation, data and model parallelism, functions and utilities to leverage some of these things are provided through PhysicsNeMo. Pre-built neural network architectures. This is what we saw in the previous slide. Um, Access to data sets, data pipes, and ETL utilities. So, taking in your simulation meshes, cleaning it up, preparing it for the neural network training. And some of these utilities are also part of the PhysicsNeMo framework. We use technologies such as ZAR, NVComp, and GPU direct storage for really fast loading of these data sets, which becomes very critical, especially when some of your even a single data point can be up to like a few gigabytes based on the simulation mesh size. Additionally, we provide utilities to incorporate physics of the problem in terms of the geometry module and the PDE losses. So these are the two ways you can incorporate the physics of the problem, which can be like specific geometry details or the specific PDE loss computations through using some of the utilities from the PhysicsNeMo library. So that covers the features, and some of these things will become more clear as we see some of the code samples later in the session today. So with that, I want to briefly showcase some of the industrial use cases that we have attempted with PhysicsNeMo, and we'll deep dive into a few of them today. So we have done a lot of work generally in terms of like CFD. Accelerating the CFD convergence or accelerating the the CFD workflow, like directly the whole forward simulation process, be it the inverse design process, and things like that. So we have done applications in automotive CFD, wind farm super resolution, in the electronics space with the heat sink designs, with the data center cooling, electrothermal cooling, and so on and so forth. In terms of weather and climate, we have done weather modeling. So, predicting weather forecasts across the entire globe or in specific regions of the globe. We have done some work with carbon storage and sequestration. We have also done some work across some other domains such as heat recovery steam generators and subsurface modeling, and also some other areas in terms of cardiovascular simulations and additive manufacturing. So this is just a summarized slide of the different areas that um, the different areas that you could model using some of the utilities and functions from PhysicsNeMo. And so today we'll focus on in the first part, we'll focus on the automotive CFD application. So let's look at some of those. So let's take an example of the external aerodynamics as an example as we go through this process, right? Most of you guys might be aware, but for people who are not aware, to set some context, today wind tunnel experiments and numerical simulations are used to do the aerodynamic evaluation of vehicle in terms of studying its performance, acoustics, and things like that. As I mentioned before, experimental analysis is still the gold standard, but is expensive to set up and costly. And so numerical simulations become a powerhouse of a way to analyze these geometries, these vehicles, and studying some of these phenomena. And so what is of importance here is solving some of these car geometries and the flow over them at really high resolution and a quick speed to enable design space exploration and optimization. So imagine you are a car designer at some of these automotive companies. You are interested in looking at different designs and seeing the effect of those designs on the aerodynamics of car, and iterate and repeat that process, and you would like to have a fast iteration cycle as you do that. And so, as I was mentioning, typically this is done through experimental analysis and numerical simulations. People like to study things like, lift and drag forces on the car, which tie into how the performance of the car is, right? Like the energy efficiency, the noise levels, harshness levels, safety and stability are all tied to some of those factors. And people also like to visualize the flow field around the car to look at the vortices and areas of high pressure, low pressure, and those kind of things. And so wind tunnels and numerical experiments have been a powerhouse for a few years now. And today what we'll look at is how AI surrogate models can also offer a valuable alternative to some of these methods. So how does one go about formulating something like this, right? So on a high level, what we'll look at today is basically developing a surrogate model for this simulation. So the idea would be starting from a geometry and boundary condition information. So for this specific problem, the boundary condition information would be the speed at which the car is traveling. You want to get to the final state, which is the flow field around the car, and you want to do that as fast as possible. Numerically, you would discretize this and solve the equations, and we'll see how these AI models can do the same. And so some of the benefits that these AI models can offer here is the faster, efficient design space exploration. Assuming that we have this trained model completed, you could quickly change the geometry, quickly change the boundary condition information, and then you could have the flow field visualized in like almost real time speed. You can also use some of these for like faster numerical simulation itself. So you can inject these AI models in your numerical solvers in a variety of different ways to speed up your numerical simulation pipeline. And having something like this, something like an AI model, which is typically fully differentiable, can enable you to do things like sensitivity analysis, can allow you to do some inverse design and those kind of things. So, right, so these are some of the applications that um, will get opened once you have like an AI model trained for something like this. So with that context in mind, I'm going to share a quick demonstration of the case study of the CAE applications here. So let's see if this plays. I'm not sure if the sharing audio, but I think that's fine. I can just talk to the video here. So what we are demonstrating here is how NVIDIA technologies come together in terms of acceleration as well as the visualization side of things. So what we are showing here is you have the physics solver application itself accelerated through NVIDIA libraries that we mentioned, like CUDA-X libraries and Warp. So think of this as your simulation pipeline being accelerated through some of these NVIDIA math libraries, and then you develop these training data sets using that GPU accelerated solver or GPU accelerated computation, and then you can train some of these AI surrogate models, and then you can plug these all of these things together in NVIDIA Omniverse, what we call, which allows you to do some photorealistic rendering and visualization of these things, and so you can basically do interactive simulations, interactive design, space exploration through some of these things as you go. And what we are showing here is this work that we have been doing with the vehicle aerodynamics space, where you are able to change certain things on the car and interactively see how the flow fields react. So for example, here you're changing the rims of the car, and the flow field um, reacts dynamically to it. You can change the geometry of the car. Here you can see the ride height is being changed, the geometry is being changed slowly, and so you're all of this is real time
So
because
this seems,
yeah.
is it parametric or non-parametric changes?
That's a great question. So for this specific one, we have these are non-parametric changes. So you can directly work with like geometry representations of the car.
STL file of the surface.
Yes, STL file or like a step file on the surface. Yeah.
And are you going to talk about the methods?
Yes, we'll talk about that in just a minute. So so we saw what these once you have these models, what they can do. Hopefully, that gives a good motivation of why someone should build some of these models. And now we'll look into some of the challenges that come when you start developing some of these models, right? And so we discussed that doing this analysis through doing this training these models on experimental data is going to be hard because it's collecting data through experiments is hard, especially because you have sparse measurements, particle image velocimetry type of data, which allows you full fluid visualization, is typically rare for like problems of this size and this design space that you want to vary. And so what we go for is like numerical simulations. And as it turns out, some of these industries, they already have a lot of data generated. A lot of automotive companies, for a variety of reasons, through compliance and so other things, they have a wide variety of data sets already generated. And so the idea would be to leverage those data sets to build these surrogate models. But what happens is, to capture some of these finer flow features, the numerical mesh or the discretization of the domain has a lot of cells, right? So you are dealing with hundreds of millions of cells in the volume, and it's typically unstructured. So you're going to have a high density of cells closer to the areas where you want to study the flow, right? So like mirrors and geometries, and you're going to have sparse cells in the other areas. And so you want to have a model that can scale to these type of meshes, these type of domain sizes, and can capture these long range and short range interactions that come with them. And so uh, we'll see how those things matter when you start designing the models for here for these domains, right? And we also want these models to be try to generalize across multiple geometries and arbitrary geometry and mesh representations. So one of the approaches that I'm presenting here, that we have been developing over the past about 6 months now, I think, is this decomposable multiscale neural operator. So if you're familiar with the idea of neural operators or the DeepONet that was popularized by Brown University, this network architecture builds on top of that. And on a high level, you have a geometry encoding network and you have an aggregation network. So the geometry encoding network is really trying to capture the geometry details given an STL file or given a geometry of the car through STL or like a step file. Um, and then use that detail along with the information of like the point cloud where you want to infer to predict the flow field on those specific points. Some of the key features of this model include, it has these multi-scale point kernels to capture these fine and coarse features. It has this iterative mechanism to capture these long range interactions. So a small change in a mirror of a car can typically change the drag coefficient drastically. And so we want to be able to capture some of those finer features. And it has basis in, traditional numerical methods in terms of it has these computational kernels to learn the nonlinear basis function. So it still has, it does like a nearest neighbor sampling and does computational stencil. So it has some of those backings in the numerical methods as well. So this is the work that we have been doing over the past 6 months, and this is the AI model that has been powering some of the demos that we just saw. So I won't go into the too much details of the architecture here in the interest of time, but I'm linking the publication here. So if anyone's interested, feel free to dive deeper here. But what we're going to focus on is more on the application side. So once you have this architecture, what we have done is we have trained this on an internally generated data set. It's a data set of steady. Yes.
Sorry to interrupt. So I just want to make sure we give people a chance to ask questions. Otherwise,
Yes.
it's late in the day, right?
Yes.
So maybe you can go to the previous slide. I want to see if people have any questions on the architecture or anything else on the methods. You can go up to the mic. Sorry.
Actually, I have just a question on other architectures. Do you guys also have support for like vision and swing transformers, which like, the Aurora model and other physics kind of foundation models have used?
That's a great question. So we have some swim and transformer type of models, and we have demonstrated that for like some of the weather and climate applications. So we'll see some of those things shortly. Yeah.
So I've read the paper. The paper is actually quite.
Is the mic on?
Is it on now?
Yeah.
So I've actually read the paper, but the paper is very scarce on details of the architecture and the training. So is there a plan to publish a more detailed paper on how Domino works?
Yeah, that's a great question. So we are working on a couple of works along those lines. So we have one is we are working on like a benchmarking paper. So this is what I'm presenting here is one of the models. We have been developing two other models, and so we are working towards publishing a comprehensive summary of how these three compare to each other. And also the whole source code for this architecture is open source through PhysicsNeMo. The training pipeline the training pipeline as well as the model architecture used here is open source through.
And any reason why you chose DeepONet as opposed to FNOs?
Yeah, that's a great question. So we found this as a more scalable approach for this particular problem. But again, this is not the only way. As you'll see soon, we have also modeled this problem through mesh graph nets, like graph neural networks. So yeah, it's just one of the approaches that we found scales well for these meshes. Yeah.
Maybe just following up. So, I mean, many people know how FNOs and DeepONets work. But so are you saying you're composing a bunch of these different networks that are segmented in some way and stitching them together?
Not yet. Right now, still these are different models, different model architectures. I believe what you're alluding is to like a mixture of experts type of setting.
Yeah, I mean, I'm just wondering, because if you're making non-parametric changes, is there the understanding of distance from the surface,
right.
I don't know how it processes that information is what I'm asking.
Yeah, I think, okay. So the STL or the geometry is, converted to what we call is a sign distance field.
Yeah, that's what I meant.
Right, and so that becomes an input along with the boundary condition information, which the network operates on.
Okay. Yeah, thank you. Any other questions on the methods? Thank you.
Yep, thank you. So yeah, I talked about the once you have like a model like this trained on a data set. So here what we try to do is generate a data set of passenger cars and the flow over them through OpenFOAM, which is like this open source CFD solver. Steady state runs was used as a numerical method. And we did this across our variety of passenger vehicles such as SUVs, hatchbacks, pickups, and sports cars across a variety of speeds from 20 meters per second to 50 meters per second, which roughly translates to 50 miles per hour to 110 miles per hour, typical operating regime for the cars. And once you have this model trained, you can do some interactive visualization, right? So as I'm showing here, you can, some of these things are hosted through the build.nvidia.com, the page that Chris showed in his presentation. And here you can see I'm changing the mirror on or off, and also changing the car geometry, and then it's going to give real-time flow field. And all of this is, real car geometry, so very high resolution meshes and those kind of things. Here, you're turning on or off the spoiler, and you can see how the flow field reacts to those changes. So that's just, an application of the model itself, right? So you have the trained model, and then you can do some of these design space explorations. But you can go a bit more further in terms of, how you can use, once you have these trained models, how you can use and leverage them. And one of the applications that we have been exploring is actually fine tuning as well as the initialization of transient CFD. So what we saw here was a model done on steady state run simulation. So it can only predict steady state flows, right? And in a lot of automotive CFD is transient because of, a lot of flow structures are transient in nature. RANS is a simplification. You typically want to do like an LES or DDES type of simulation. And so what we are seeing here is, even though this model predicts steady state simulations, you can use this as an initial guess to start your transient simulations. And what we have seen is you can get orders of magnitude speed up in your transient solve. So your transient solutions are going to converge much faster because it is starting from a much better guess. And of course, the way to compute that guess is almost at a fraction of what a typical RANS solve would be. Yeah, that's a great question. So right now, what we are released as a checkpoint and what is usable, you can only change the velocity and the car geometry. But one could also, like, since coming from an architecture standpoint, yes, you could change if you had like a data set where you are varying the viscosity of the car or the density of the air around the car, those changes can be included. But yeah, this trained model right now is not doing that. So yeah, one of the applications is faster convergence of transient CFD. Also a lot of fine tuning cases, right? So think of like we have this trained on a wide range of car geometries, but if you wanted to fine tune this model on, let's say, just the sports cars, one could do that, right? Like you can do a fine tuning study. So that's some of the applications that we have been exploring. These are some of the other works that we have been doing in terms of pushing boundaries of what can be done. So some of the other models that are being explored here. This was the model that I was alluding to, X Meshcraft which has backing in GNNs, and you have this other one. We are calling it FigNet. Which uses yet another method to model these. And in all of these methods, the fundamental motivation is the same. The model should be able to capture some of these large meshes and define features that come along with them. So that was one of the applications that we saw that we are doing with the automotive CFD. Now let's look at one other one, important one that we have been working on for a few years, which is this weather and climate. So again, to give a high level context of this to folks here, simulations are used widely in this weather forecasting community as well. A lot of forecasts that we see on our phones are coming through numerical simulations that are run at these supercomputers at these meteorology centers, right? So about around 180 of weather modeling centers across the globe are constantly running these simulations of the atmosphere, using the current state, trying to predict the future states of the weather. And one of the very important things in this domain is generating ensemble forecasts. So weather, as you might know, is a chaotic system. You have something called as a butterfly effect. A small change can lead to a large variation in the weather pattern, and the initial conditions are typically, not exact. There are measurement errors because your measurements are coming from satellites, weather balloons, very sparse measurements. They can have some inaccuracies. And so typically what in this community people do is they do something called as ensemble forecasting, where they take this initial condition through the best means possible, and they perturb the initial condition by adding some noise, carefully calibrated noise, of course, and try to run the simulation one more time. So you can see that you want to run this simulation for, let's say, 50 times to build like a 50-member ensemble. And then you want to build like a probabilistic forecast. And so traditionally, each of these is a single simulation run, right? So most of these simulations are run on supercomputers and are very expensive. And so you now become limited by how many ensembles you can, run to do this in a computationally efficient way. And so what AI models offer here is, again, due to their ability to do fast inference, once, of course, you have spent enough time in training, is, your inference is almost very fast. Typically you can do it on one GPU. And so that allows you to develop these large ensembles, which can enable you to capture some of these low probability events, like, um, extreme weather events and those kind of things. So basically, you can generate massive ensembles through AI generated models. And so I'm going to share a couple of works that we have done at NVIDIA in that space. So one of the early works that we did, I think about 2 or 3 years ago now, was this ForecastNet, uses an adaptive Fourier neural operator. So it combines basically the best of AI and physics in terms of, it uses transformers as well as these Fourier neural operators, which are well suited for some of these physics problems because of their global convolutional nature. And you know, this model basically was trained in an autoregressive fashion. So the task for this model was, given a weather at time t, predict the weather at next 6 hours. And so the model, once trained on this task, you can feed in the model's predictions back to it, and then it can keep generating forecasts in future, right? So t+6, t+12, t+18, so on and so forth. The data that was used for this was this quarter degree global weather data provided by European Center for Medium Range Weather Forecast, ECMWF. And the data used was from 1980 to 2018. So again, this is another application, another example of an domain where large amounts of data are already available to leverage from, because there are past historical data, historical weather measurements, and reanalysis data that one can leverage from. And so here what we are showing some of the results is, once the model was trained, it could predict to a good degree, to a good time horizon, about 48 hours to 72 hours, some of these key atmospheric phenomena, right? Like the hurricane tracks and formation of some of these typhoons and hurricanes, which are important from energy perspective, from safety and those kind of perspectives. So it does a fairly good job in terms of predicting the weather in future states. An extension of this was like released about a year ago, which we call spherical neural operators. So here, we are taking the AFNO further by adding spherical Fourier neural operator. So this is again the implicit bias that I was mentioning about the problem, right? So we know that our globe is spherical, and so the previous model basically treated the globe as a 2D representation, and what that led to is you have this your poles at poles you're getting this stretching, and so you're trying to kind of basically avoid that through spherical Fourier operators, again designed for operating on spheres. And um, what what uh, what was found with this is you could do a lot more longer and stable rollouts. So where AFNO, the previous model, failed for, let's say, like a 6-month time horizon, uh, the SFNO was able to provide more stable, more consistent predictions. Of course, as I alluded earlier, it's a stochastic problem, so the flow fields are not going to match exactly. But the key here is that the structure is present, and um, probabilistically it looks reasonable, even on a 6 months or to a year time horizon. Next, we'll look at how diffusion model can be useful for this particular application. Um, Diffusion models, more specifically denoising diffusion models, start off with are really good for producing uh, images or producing representations that are similar to a given data set, right? So it is um, it does a very good job in that, and it also does a very good job in terms of like super resolution and fine tuning, those kind of fine grain predictions. So we'll see how diffusion models, and more specifically denoising diffusion, can be helpful here. And also the fact that these diffusion models basically start off with a noise and basically progressively denoise it to get the final output. One can really see that this can be very useful in terms of like with this weather example, where you are inherently generating like an ensemble of predictions, right? So you want to have some sort of uncertainty in your predictions. So these again become a good option here. So I'm going to dive a little bit into the theory of denoising diffusion. Oh, you have a question? Yes.
I don't think so. Oh,
Yeah, I think it's
maybe
good.
it is. Couple quick questions on the previous weather modeling. So first, I'm curious how you approach kind of splitting up your data into train versus test, and what impact you think that had?
Yeah, that's a great question. So I think the idea here was to use as much training data as possible. So at the time of that research, I think ECMWF had released up to 2018 of data. And so what was done was we kept 2 years for testing, and the rest of the was used for training. And then for validation, or rather 2 years was kept for validation, and for testing, you have some of these other sources of data set that are more recent, and so we just leveraged those for testing of the models. Yeah. I think the mic turned off. Yeah.
You motivate this by interest in kind of these low probability but high impact events. So I'm curious, do you ever look at kind of whether or not kind of directly does your model get that right compared to some reference?
Yeah, that's a great question. I think in a deterministic sense, it comes close, but of course it doesn't match exactly. And I think that's where we are looking at these probabilistic metrics to better evaluate some of these things. Yeah.
But I guess like, does it get the probabilistic metrics right? Like, if that makes sense.
Yes. So yeah, we do evaluate some of these things. I'm not sure if I mentioned that here. Yeah, but we do evaluate some of these things on like metrics like CRPS, which is like continuously ranked probabilistic statistics, right? And ACCs. So some of these measures are typically found in atmospheric and weather sciences, and they evaluate these methods exactly on that, like how well are the predictions doing in probabilistic sense. And so yes, some of these models do come very close to some of the industry standards, which is like this IFS, I believe they call it. I'm, I'm, I don't know the exact abbreviation, but I think it's like
It's ensemble, yeah.
yeah, IFS, which is a numerical model, right? And so the results of these do come pretty close to some of those results as well. Yeah.
Storm trajectories, intensity, and things like that. And most of these models these days are able to get close, state-of-the-art models. This is one application where these models are somewhat trustworthy. Not all applications, but this is a sweet spot, in my opinion.
I also have some questions, but to react to the previous study on the flow around cars, can you comment a bit on the accuracy of your infer solution? Because you use numerical simulation results that have some errors.
Right.
So, how is the error of your infer solution compared to the base solution that you use for training?
Yeah, that's a good question, and I'm going to talk about that in a little bit. But also, yes, we do capture that. Yes, the model is only going to be as good as the data it is trained on, unless we add like specific physics-based constraints, which we'll also talk in a bit in the subsequent slides. But yes, since this was purely data-driven, your models, your model is going to come only close to the data it is trained on. So in this particular case, yes, the predictions do come very close to what a steady state RANS solution would predict, like the model's inference. But we also know that that's not the final result, and people go beyond that. And that's some of these other studies that we are showing here is how you can use that to initialize your more advanced and more accurate models and still get like faster convergence on those things, like basically like a transient study and things like that.
And you also mentioned that you're using, I think there was a parameter of speed or a range of speeds. Or I'm wondering, can you go beyond that in your inferred solution? Like
Yeah.
You mentioned 5 to 12 to 20, but when you infer, can you go outside of that range?
Yeah, that's a great question. So that comes to the generalizability of the model. So I don't think we have tested it beyond these speeds, but of course, I think the performance is not going to be as good as what it would have been in that range. But yeah, I think we I don't have the answer to that. Yeah, unfortunately, yeah. Yep. Yes.
I was wondering, you said that you trained the weather prediction from data from 1980 to 2000, and you took 2 years out for your training or for your test data. I was wondering if you had any concerns about like certain long-term changes and how the model may be biased against those, such as like climate change, which especially impact like the probability of high impact, low probability events.
Yeah, that's a great question, and that is, I think, a thing to look out for when you train some of these models, right? Like there have been changes on the climate scale that you need to be cognizant of. There is a step that typically is done in these models, which they call it as a bias correction. So you evaluate these bias and you account for that. So that is one way to account for something like that. But again, there is also potential for like fine tuning it based on the more recent data to nudge it more towards current weather patterns.
Were you guys able to like test your prediction accuracy for those high impact, low probability events over different time frames to see if they got more or less accurate in a given time frame?
Yes, it does. I think I don't have it here, but I can share with you offline. But there are a few blogs that we have published where um, it was able to predict the heat waves in Algeria. I think back in 2020 or 2018, um, because now you could now do like 1,000 member ensemble, and if you had just done like a 50 member ensemble, you would have missed that. And so yes. We have shown this, I think more, we have shown this in like from the examples in the past, I think that the extreme weather events that have happened in the past. So, yeah. Yes. Mhm. Actually, no, not yet.
Yeah, no, it's not so.
Yeah.
So in this work, you're training on the CFD data, but the application, I think the way I'm understanding is the application is towards using it on a unknown surface data. You're using the STL as an input, but what if this STL is, not a watertight surface, and it's a broken surface? It may be the intersecting surface. How does this model handles it?
Right. Yeah, that's a great question. So that is, I'm great that you brought that up. That is one of the limitation today. So we do expect that the geometry is clean, is watertight at this point of time. We are looking into, ways in which you can circumvent that. Inherently, this is using point clouds. So we are not generating meshes. So, you are able to generate point clouds on like, fairly unclean meshes as well, at least on the surface. Volume point clouds is where you need these watertight meshes and those kind of things. But that is work in progress. But right now, the train model that we are shipping does require you to have a watertight STL.
And not like they're just overfitting to the data.
Yeah, that's a great question. Especially for this particular application, we just tried it on a variety of different passenger car and most prevalent types, right? Like so pickups, sedans, SUVs, and those kind of things. And so we had a bunch of unseen geometries from these classes, and we tried it on that, and it does a good job. And so of course, this is not going to work on a completely unseen geometry like a semi or something. It will predict something, but chances are that the accuracy is going to be very low. But since we trained it on a variety of different passenger cars, we have a good confidence that given any different passenger car, this is going to perform well. And based on the test geometries that we have tried, it does a good job there. Yeah. Okay, so if no more questions, I'll continue on. So yeah, we're gonna look into the diffusion models, especially the denoising diffusion models, and how they can be applied to some of these weather forecasting problems. So I'm just gonna quickly cover what denoising diffusion looks like. This is not gonna be a technical deep dive, but hopefully just gives a rough idea, right? So here, what we are showing is on x-axis, you have, think of it as a pixel space, and on y-axis, on y-axis, think of it as a pixel space, and on x-axis, think of it as a level of noise added per time. And what we are doing here is we are taking an image, and then we are progressively adding noise to it till a point that it becomes completely white noise, right? So that's the extreme on the right. And what denoising diffusion does is basically the philosophy is that it is way easier to sample from this space of a uniform normally distributed Gaussian noise, and then assuming that we could do this step-by-step denoising, you could retrieve the original image. And so the idea here is that if you have a data set and if you had added noise to each of that data set, all of those images are going to eventually converge to a uniform distribution of noise on the right hand side of the plot. And then you could sample anywhere from there, and then you could progressively denoise it. And then basically you can generate similar looking images that are in your data set. And these type of models are the backbone of some of these works, image generating models, right? Like the DALI and from the OpenAI models. So that's on a very high level how these denoising diffusion work. And these models basically are formulated either through a stochastic differential equation or an ordinary differential equation. And then the probability distribution function is approximated through like a neural network, right? So you have like a convolution neural network or a transformer based neural network over here. And then you're going to train as a part of training, you are training the model to denoise the image slightly. So going from a slightly noisier image to a slightly less noisier image. So turns out once you have that, you could use the models. Those type of models can be used for things like spatial super resolution and those kind of things, right? So one of the works that we are showing here is this correlative. We call it as corrective diffusion model, and this model is trained to predict kilometer scale simulation on just a region over Taiwan, given data from a 25 kilometer scale, right? So assuming you have 24 kilometer across 24 kilometer grid and the data on that grid, you want to go to kilometer scale. And of course, a higher resolution forecast is much better because you can study the finer features in much more detail. And so what this model does is it uses like a two-step approach. It takes this idea from Reynolds decomposition, where you have a mean component and you have a stochastic component, right? And so the mean component is modeled through like a regular regression model, like a UNet or transformer model. And then you have this diffusion model to predict the finer scales. And so a combination of these two can be then used to generate finer scale forecasts. So this is one of the applications of this diffusion generative AI model for super resolution of weather patterns, right? And so this is, yes.
You're using a new set of data for the super resolved field.
Yes. So the data is two set. One is the kilometer scale coming from, again, the same ERA 5 data that was used for AFNO. And then we have kilometer scale data just on Taiwan coming from Taiwan Meteorological Agency. And the model is basically trying to create a mapping between these two.
The boundary conditions for the super resolved set is how are they handled?
Yeah, so this does not handle any boundary condition. It's just temporal snapshots in space. So this is another result showing the same on continental United States. Again, this is part of that build.nvidia.com, so one can play around with this, try to throw in some date and time of your choice, and then play around with it, and you can see how you can have like a slider to see this model in action, basically super resolving the flow fields. And you can see on the right, on the left, you have a much higher resolution. On the right, you have much lower resolution. So those are some of the models and architectures that are available in PhysicsNeMo for using today. There is more active research happening in NVIDIA research as well. Yes, you have a question?
Can you hear me?
Yeah.
Yeah. So if you have these high resolution data available, what is the point of doing this super resolution in the first place?
Yeah, so that's a great question. So the idea would be to do this high resolution in future. So you combine this core diff type of model with some of these forecasting models that we saw earlier, like AFNO or SFNO. And so you typically don't have that high resolution data at like the future time states, right? And so you could use these global models to generate future forecasts that is at 25 kilometer scale, and then you super resolve it for future, right? So it turns out that is a much cheaper approach than training a forecasting model for that full super resolution, right? Because that creates, I think, just at 25 kilometer scale, you are talking about 700 by 1040 type of a pixel image, right? And you're not just dealing with one image here. You're dealing with like pressures at different atmospheric levels. You are dealing with temperatures. So all of these are represented as channels. So even a single time snapshot of this weather at 25 kilometer scale can be huge. And so that basically makes it expensive to do this on a much finer scale for like a forecasting scenario. And so what this does, the idea here is to use these two in combination, where you use the low resolution forecasting model to predict in future, and then you use this generative downscaling model to downscale each of those forecasts.
You could use multiscale diffusion models, I think.
Yes, that's a good question. That's a good point. I think some of these newer works, like the climate in bottle that I'm showing here, are kind of trying to do that, like basically high resolution diffusion model directly for the full globe. Yeah. Yes. And also to mention to that, like high resolution data for the full globe is not available typically. So, if that type of model has to be developed, it will be like a region specific model. Yeah. Yeah.
And you can get like weather patterns from far off regions at low resolution and then super resolve where you need to as well. Yeah. Misha?
I would like to get clarification on, well, diffusion. In diffusion itself, time is artificial, right? So it's not a physical time.
Mm-hmm.
So you are, well, generating sample which is both in space and time, correct?
Yes. The time here is not the physical time. Yes.
Okay. So did you think, or did you try to actually make it in a physical time? So diffusion model in the physical time.
Yeah, that's a good question, and that is we're calling it as lead time aware diffusion model. So where
How can you repeat?
lead time aware. So the lead time is basically how long are you forecasting, right? So is it, are you forecasting for 6 hours versus 12 hours and those kind of things, and how it relates to those diffusion scales. But I believe that is still in progress, the work in progress. Yeah. So so that's some of the latest research coming in, and we are hoping to make this available through PhysicsNeMo soon. Today you can find them through these publications. I think the Stormcast is already integrated and available through PhysicsNeMo, and we are working on the climate in bottle model here. So just to summarize quickly here, right, like the different models that are specific to this weather and climate domain that can be accessed through PhysicsNeMo. And I talked about this implicit bias and these models that are rooted in physics. So this is a very good example here. You can see a lot of these models are basically coming up with novel ways to capture the spherical geometry, right? Rather than just representing it as an image, you have this DLWP cube sphere, which instead of splitting the globe as an image, it splits as a cube. You have this Hillpix grid. You can represent the sphere as an icosphere. You can use spherical Fourier operators and so on and so forth. And so we have other models as well that are part of the GitHub. And we talked about the regional super resolution models. So with that, hopefully that got you interested in the variety of applications that AI can do and what PhysicsNeMo can offer. And so now let's dive deep into how some of these things can be done through PhysicsNeMo and looking at some of these things in action. So we're going to take a simple problem and walk through that and see how features from PhysicsNeMo can be used to model some of these problems. Right? So we'll take a simple problem. The idea is to model a Darcy PDE. It's like a diffusion equation over 2D, right? Simple problem for understanding. And what we'll assume is we have a data set of input-output pairs, right? So basically think of it like you have this PDE that is shown here. You're varying these input coefficient fields, and for a fixed forcing function, you are getting different solution fields if you solve it through a numerical solver. And the idea would be, if you had such a data set, train a model to develop a mapping between these two. So one can claim that if the model is able to predict that, the model has captured the physics of the problem, right? So that's the kind of the mapping that we are going to try to develop here. And the architecture that we are going to use here is FNO. The exact details of the architecture don't matter here. One can even train a CNN for this simple problem, but FNO has some very nice properties of like global convolution, which turn out to be more useful for this type of problem, right? It gives better results. But for this demonstration, I think the architecture is not that important. And so this is what a typical training of a surrogate model pipeline look like today in PhysicsNeMo. So you start off with this data. That data can come from solvers, like your simulation tools, or it can come through experimental measurements. You collect them to a database, and then you pass it through these optimized data loaders that we have and ETL. And through that you pass them to your model to do the training. The model can be trained on a single GPU on multiple GPUs in terms of like a domain parallelism. And then once the model is trained, you do the inference on the model, right? So the inference is typically real time, like any other applications of the AI models. So I think for folks who are familiar with writing PyTorch code, this will look very similar, right? So this is what writing a code with PhysicsNeMo would also look like. You can see it's very similar to PyTorch code. You have your Python imports, you are loading your data, you have your model being defined, you set up your optimizer and parameters, and then you write your for loop, right? Which is the training loop, which iteratively refines your model's parameters. And at the end, you save the model checkpoint every so often. In this particular example, we are importing a few different utilities from PhysicsNeMo to aid this process, right? So for this particular example, we are importing the FNOs from PhysicsNeMo. We are importing some of the logging utilities, and we are importing the checkpointing utilities from PhysicsNeMo, while the rest of the code is still very PyTorch specific. And so, this is one of the simplest example in which how you can import things from PhysicsNeMo into your workflows. Like, use the wide model zoo that we have available that we just showed before. And so you can see how it's really interoperable with your PyTorch code. One of the next applications that we'll see is physics informing these models. So a lot of these problems are, I mean, by now you must be aware, is have some rooting in partial differential equations. You know, there are some governing equations that have been executed by the simulator to come to that answer. And so it would be nice that the model prediction kind of respected that. And here at PhysicsNeMo, we have taken a few different approaches. One of the approaches is basically adding like a regularizer function that explicitly tries to enforce that constraint, right? So think of like Navier-Stokes equations or like diffusion equations. The PDEs are imposed as loss functions in your overall loss. So through PhysicsNeMo, we provide ability to add these physics type of constraints on almost any type of neural network model. So your model can be operating on point clouds, it can be operating on like 2D grids or 3D grids, or it can be operating on meshes. And so we allow you to compute these physics-based losses through a variety of different numerical methods as well, like through autodiff, through spectral derivatives, finite difference, meshless finite difference, least squares, you know. So basically you can choose what works best for your data representation, your model outputs. And so using some of these features, we have physics informed a lot of different types of models, right? Like MLPs, DeepNets, Fourier neural operators, CNNs, diffusion models, mesh graph nets, so on and so forth. And what I'm showing here is some two different ways in which we have seen adding physics-based constraints have improved the training and validation accuracy. So on the picture on the right here is, or on the left here is showing a mesh graph net model trained in a data-driven fashion. So in the middle, you have a mesh graph net model, model's prediction when it is trained just with data. And so you can see it tries to get the larger scale features, but it still has that noisy, it still has some noise. It's not able to do a very good job given the data set it has. And so what we can do is we can add this physics as a fine tuning step and then enforce the predictions to be more physically consistent. And so on the right is that fine tuned step with the addition of physics losses. On the right, the picture shows another use case where we have added this physics loss as a part of training itself. So you have the data center use case that I alluded to earlier, that is being modeled through units, and you are adding physics losses, and you can see that the training and validation losses both decrease as you add these physics-based constraints. So these are some of the ways adding physics can improve your accuracy of the models. And so that's adding physics losses in terms of PDEs. You can also incorporate geometry information. So a lot of these problems in this space of physics AI have like geometry representations, and we have variety of different ways in which you can represent geometry, right? So we have this constructive geometry module, which allows you to compute like point clouds and those type of representations by composing primitives, right? So you can compose these primitives like cubes and spheres and cylinders and form some of these complex geometries. But that can be like, we don't aim to provide like a full-fledged CAD type of capabilities. And so for that, we have for like some of these more complex geometries, we have also support through STLs. And you can compute sign distance fields. You can plot point clouds on the surface, point clouds on the interior, using some of these utilities, right? So allows you to do implicit geometry learning through some of these things. And so how does adding physics losses look like for the same problem? Here, I'm going to omit some portions of the code that are common from the previous example, and we'll see we are importing two more things. One is this diffusion PDE. So PhysicsNeMo has a collection of PDEs that we have already written out and validated, right? Like, so some of the common PDEs are already available for you to like directly import, like diffusion equations, advection diffusion, Navier-Stokes, electromagnetic Maxwell equations, and so on and so forth. But you can also write your own equations and bring in your own PDEs. And so by just a matter of few lines, you can define the parameters of your PDE. You can create a loss function through it. Here I'm saying that I want to use finite difference as a method to compute my gradients. I could choose here autodiff. I could choose here any other method that I talked before. And basically you can just add it as an additional loss term in your overall loss, right? So you have the data loss, which is nothing but a L2 error between your output prediction and the true output. But additionally, you're imposing this differential equation that it needs to satisfy the diffusion equation. So this is one way that you could incorporate physics loss in the example. One other thing that I want to cover here is the domain decomposition capabilities. So in a lot of times, you will notice that a single simulation mesh is about hundreds of millions of cells, right? And in those cases, even a single mesh cannot fit on your GPU memory. What that means is even with batch size 1, you're not going to be able to train the model. And in those type of scenarios, what people typically do is like a domain decomposition type of problem, right? So it's from a numerical computing standpoint, you guys must be familiar, right? Like splitting of domains into multiple chunks for each processor to process is very common. And so what we do through this here is provide that mechanism to do that for these AI training as well. So you can decompose your input data and train it on multiple GPUs so that you are not bottlenecked by the VRAM capabilities of a single GPU, which might not be enough to fit a single simulation. So again, this builds on PyTorch's FSDP framework and provides ways to do domain parallelism for these type of problems. So again, a simple code snippet that shows how you can go from a single GPU implementation of a convolutional kernel on a input tensor to doing like a distributed data parallel version of the same operation, right? So importing some things from PhysicsNeMo, like the distributed manager and the shard tensor. You can set up your problem to run in across multiple GPUs, and then of course the results are going to be equal. So that's another example of how domain decomposition can be useful. Some of the other stuff that we are working towards is I think there was one question earlier, how well do these models compare to the simulation? So we are working towards releasing like this benchmarking workflows that will be hopefully useful for a variety of different CFD applications. And so we're trying to provide utilities to evaluate some of these models on some of these complex metrics, do some fine-grained analysis of these models and look at some of the metrics that are really important to the industry, right? Like the design trend analysis and things like that. So that's the code for this should be out soon. It's not yet out, but I would just say stay tuned. The initialization workflow that I talked about, like the initialization of transient flows through these AI models. Again, that is we are looking to release that as a code sample so that you can try that out, incorporate that in your workflows. Again, that should be releasing soon. On the Earth-2 side and the weather and climate side of things, we have this package called Earth-2 Studio, which you can use to do some of these. You can play around with these models, right? Like you can do take some of these trained models. We do ship these trained models through variety of different mechanisms. I would encourage you to check out this repo, and then basically you can play around with them, right? Like forecast weather 10 days in future, and then this repository allows you to do that. So wrapping up, PhysicsNeMo, how can one get started? In terms of like using the software, we do ship it in 3 different formats. One is a Docker container, very ideal for enterprise users who just want to get started quickly without much setup. We also offer Singularity support. A lot of university clusters do not allow Docker for security reasons, so you can use it through Singularity as well. We are very well into Python ecosystem, so you could also install PhysicsNeMo through PyPy. It's very composable. Like you have a lightweight version of PhysicsNeMo, and then you can compose based on what features you need. So like example, you just need SFNO, so you can do like a PhysicsNeMo Makani install, Fignet, and so on and so forth. And then last but not the least, we are open source on GitHub. So this is also available via GitHub. We are open source via Apache 2.0. So, very less restrictive licensing here. And we are also accepting external contributions. So if you think you guys have some cool model that you would like to share with others, please do reach out, and then we can bring that in through PhysicsNeMo. Going ahead, what are some of the resources that you can look at to learn more about PhysicsNeMo? We have a teaching kit which was developed in collaboration with George Kaniadakis at Brown University. It's available for instructors and researchers to incorporate that in your coursework. It includes video recordings, lecture slides, notebooks, projects, and it goes beyond PhysicsNeMo. PhysicsNeMo is just one module in that, but it also goes about like in general theory about physics AI in that. So that's a good one to look at. We also provide self-paced DLIs. So some of these specific modules like weather applications, we have it as a DLI that you can look at and learn. And we also do these boot camps every once in a while, where we provide some compute, and then you guys can basically test these things in a live environment and play with the examples. So with that, I'd like to end here and take any questions. Thank you very much. Yep. Questions?
All right, now the lights on. Okay, yes.
So you had these physics losses. These are all soft constraints.
Yes.
Do you either have hard constraints in these models? Because my understanding of the models, as my current understanding, is that they don't. So if not, do you have any plans to add hard constraints?
Yeah, that's a great question. So we have explored hard constraints for certain things, like adding boundary conditions. Adding something like a full PDE as a hard constraint is much more challenging. So we don't have too many examples of that, but we have tried that with like boundary conditions. So like for example, explicitly imposing periodicity or like Dirichlet boundary conditions, or those kind of things can be done through
Something like within the bulk, making sure energy is conserved,
Right.
or it doesn't look like you have distribution, so you don't have entropy,
Right.
but nothing like this.
Yeah, no examples for hard constraints in the interior yet. Yeah. Yeah.
How do you imagine they'd be imposed?
So my background's in physics, so I'm gonna come at it that way.
Thinking symmetry, or how else would you impose it? Framework.
I would impose it kind of thinking about a diffusion model. You have a lot of physics baked into it, and then there's this one term, this error term, that you use a unit, but the physics is already baked into it. And so leveraging.
We want to take a differentiable physics approach where the whole thing is automatically satisfying the conservation laws and then add corrections. Yeah.
That's a good approach. Yeah.
My question is also related to the physics loss. You have also a data loss, right?
Mm-hmm.
So if your data comes from numerical simulation, aren't you over constraining the problem because your data has a knowledge of physics already,
right.
And you add a physics loss,
right?
So is that not too much?
Yeah, that's a great question. And yes, we do have to be careful when you add something like that, because there are two things. Yes, you might end up over constraining. So as you would have seen in the previous example, you have like this Lagrangian multiplier, and that is a hyperparameter that you have to typically play with, like to control how much data versus how much physics loss you want to have. But also there is another key important factor that one needs to be aware of is even these numerical solvers might not be satisfying some of those PDEs exactly, right? So you want to be really careful how much you want to constrain based on the physics losses, because you might say that the momentum, the mass balance is 0, but your data itself might not be respecting that, and so you don't want to create like this challenging environment for the model, right? Where it's trying to learn from data, which is not respecting the continuity, but you're also trying to impose it explicitly. So you have to be careful there. And so one of the applications that I showed is where you do it as a fine tuning step can be an alternative as well. So you do add the physics losses on in like the fine tuning process of the training.
Yeah. And also, if you add a physics loss, you also need to know what physics governs your problem.
Right.
So what if you don't? Do you not add a physics loss, or?
Yeah, so as I mentioned, the physics loss is an optional thing. So yeah, you don't, if that is, so for example, a lot of these weather models that we showed, they're trained purely on data because the physics is difficult to capture. There's a lot of subgrid scale modeling involved. So we just let the model learn from the data.
Thank you.
Actually, back to physics. Well, there are some suggestions about including physics and specifically fluid mechanics type of physics, not in a score function, but working with reduced models, right? And parameterizing certain parameters, let's say diffusion coefficient, maybe constitutive equations, that type of things, through neural networks, right? So it is a kind of paradigm. Did you guys try to, well, put it in a general form? So it's like if you're talking about, let's say, Navier-Stokes and a particular type of, so it will be already specific, a particular type of model reduction of this or that type. If I can, jump and use it already, prepared.
Yeah, that's a great question. We have explored some ideas there in terms of like, I think there was this paper early in this space back in 2018, 2019, hidden fluid mechanics, where they tried to infer out like the Navier-Stokes equation from the data itself, right? Like the coefficients in your equations. And so yeah, some of those type of things can be done through PhysicsNeMo as well. But yeah, those are like very specific to the data set and the problem. So we don't have it, generally packaged recipe of some sorts, like what we have for some of these other use cases.
And then maybe another sub question. If you are again, if it is fluid mechanics, and you mentioned at that moment flexibility to solver, right? So you can use different solvers.
Yes.
If you have some Lagrangian solvers, particle-based Lagrangian, like smooth particle hydrodynamics, or like
Right.
If you considered integrating it in your package?
Yeah, so that's a great question. And so maybe I'll jump to the GitHub for a second. So we do have some examples of Lagrangian solvers. We do have some examples of Lagrangian problems that we have attempted through PhysicsNeMo. Let's see if I can pull it up. But it was done through a mesh graph net, and we did it in a purely data driven fashion. But yes, you can impose some of these constraints like causality and those kind of things in there. We don't that will become, I think, application to application specific. We don't have a unified way of doing it, but we have explored that from a case to case basis.
Hi. Yeah, I have a question. Actually, two questions. My first question about this physics thing for neural. So, is it possible to use that because I noticed that most of the training data set are running from the static case. But like, how can we deal with the unsteady case? Like, can you train with a steady data, but then can you predict any unsteady phenomenon when you use that?
Yeah, that's a good question. I think if the model hasn't looked at like unsteady simulations in their data set, it's going to be hard to predict something like that. And that's why we have taken one of the approaches that I showed before, where you kind of use the steady state prediction as an initial starting point. So you can, and then you can have something like what we have done with the AFNO, which is an autoregressive model that, given a current state, it evolves it in time. So one could do something like that to get to even have like an AI model to give you that transient rollout. But yeah, there have been some research ideas exploring that, but yeah, we don't have that in the PhysicsNeMo yet.
Thank you. My second question is about the application of use this PhysicsNeMo. So is it possible for the users to like doing any adaptive sampling during the training process? Like can you do adaptive sampling instead of you sample all these points like at the beginning of the training?
So adaptive sampling in terms of the space, or in adaptive sampling for your data?
Yeah, for the data.
Oh, okay. So we do have some adaptive sampling algorithms for like spatial sampling. So if you want to sample like point clouds, we do offer some of those capabilities. In terms of sampling from your data, I might have to check. I'm not quite sure. Yeah.
I think maybe your question, and then we'll sort of jump into the office hours. I guess whoever the earlier tutorial, and then I don't know if Sean is still here.
Can you talk a little bit more about your benchmark? So, because just talk about the CFD, right? So you have a different solver, you have a K omega, K epsilon, and you have your solution. How did you, are you trying to like build the like 10, 20 different use case to allow people to compare? I mean, what is your benchmark framework looks like? Curious.
Yeah, so that's a great question. So as PhysicsNeMo, we are not necessarily too much into providing this fully fledged end surrogate model, right? Like we have done that with like some of the weather applications because that's more universally applicable. But with this type of applications, the goal is to mainly provide the access to the training pipeline code, right? So the goal is to provide access to the model architecture, the training pipeline code, and then the with the domino checkpoint, what we have done is hopefully try to demonstrate how something like that can be done, assuming that you had that type of data. But developing something like this, that's not what we are after. Yeah.
Okay, we will now head to the last session, which is office hours. This is actually the best session, so everyone in the back, feel free to come and take these reserved seats that are now no longer reserved. Have an intimate chat, so I think it'll be pretty exciting. So maybe I'll kick things off, and I'm going to ask you, Sean, a question to start us off. So yeah, thanks for